Hello everyone, this is a video for KV7006 machine learning module. I'm Nanling Jim. Today's topic is about the classification trees. Normally we also call decision tree. I think most of us probably have already seen something like this before. So there are two examples. For example, we have looked at the left diagram. We have certain features. Features is something we use to describe the object. For example, size or width, length, etc. On the bottom line, you will see there are classes. So in this example, we got the type 1, type 1b, type 1c, type 2. So in most cases, classification are exclusive. Okay, so which means if one object is in 1A, it will not in type 1B. So they are exclusive to each other. However, we also know that some categories have some overlaps, which in recent research, they have some classification which it might be one object might be in one class. It could be also in some ability in another class. However, that is out of scope for this lecture, for this video. So we only consider situations where our class value are exclusive. Okay, so let's look at the first tree. So I got one features which has certain values. Okay, so we can divide them to not h. So this is a variable which has two values. They are binary, h and not h. So they are values of this feature. So because not h and h are exclusive as well, so we can divide them to two branches. So our dataset, anyone is in Sn value equivalent to h, will directly go to type 2. Okay, so if this object has Sn value not h, they also look at the other variables, for example Si. So this is about astronomy, so we don't care about what the Sn value is, meaning is. So okay, and then again, if so on these two, so Sn has complete, we divide them to two parts of dataset. Now we look under the condition Sn which has a value no h under this dataset, we further look the other feature, for example Si. So they could be Sy equivalent yes or no. So we further divide it down. Okay, so basically we use different features to divide dataset, and then we try to divide the dataset, and then we try to find what the most relevant class this object would be. So these are based on historic data. So we are machine learning model will learn or establish this tree. So because classification is very decision tree or classification tree is a very typical ways of classify objects. So many machine learning packages in different program language, Python, MATLAB, all have these packages. Okay, so we look at another example here. It's a similar. One object have some events. Okay, you can also depend. This is also binary, so you can also separate them further separate it down, not yes, and then you further separate it down to different classes. So end of the day, a new object come in. Imagine we got a new object which is not in our historic dataset. What is probably class it would be? So you put this object in, check different features, and finally you find one classes which belong to. So in future, I'm going to cover how are we going to measure the accuracy of classification trees, classification. The reason is some models are good, some models are not. So we probably want to know how are we going to evaluate such model in a statistical way. So end of the day say, oh, I have learned this model. So accuracy or other measures would be, for example, a false negative, false positive. You probably have heard a lot recently in the news paper about the COVID virus test. So there could be false negative. So this patient has a virus, but the test shows he's free. He has no test. So that is false negative. Okay, so that is quite dangerous, right? So we need, in this case, in the COVID test cases, we need to pay special attention to those who actually had the virus, but the test result is negative. Negative means normal. So we will cover the measure in a different video. Okay, let's move on classification trees. So this slide gives you an idea, understanding better the principle or underneath a theory of a classification tree. So the aim is to determine which variable, which features are the best, separate the observation into labeled group, label them into class. What do we mean by variable or best? So let's look at the previous slide. So maybe in the dataset, so in this case we have 1, 2, 3 features which we generate this decision tree classification. However, in reality, probably this dataset we have 100 features. Okay, but these trees only have 4 features out of these 100 features. Therefore, we probably only choose relevant variable, not all variable, to represent a tree, which should be most accurate in a simplest way. So this is also relevant dimension reduction. We will explain in different video. Okay, so basically we divided prediction space into different hyper triangles. Okay, any observation in a hyper triangle predicted to have the same label. Put in a simple way, if we have, the whole search space is large. However, if we divide it to subspace, we are able to give them a class. So basically, we put all data set into 4 classes, 4 groups, okay, into the groups with same label. The best way to split is to maximize the purity of the hypertriangulars. In another way is, because the historic data, I already have these class labels, which already know. Human experts have already labeled them. So we treat them as ground truths. Okay, so the purity means that in my type 2 group, okay, given this decision tree, compare this one to my real data set, which expert has already labeled. Are there 100% type 2 which record has SN equivalent to H? Probably not. In most cases, the purity cannot be 100, otherwise it's overfit. So what does it mean? It means that, imagine I've got a historic dataset, okay, with all records, with all features and class label. And then we learn from that and make a decision classification tree. Of course, I can generate more than one classification tree, depend on the dips. So because imagine I have 100 variables, features, I can generate a tree with 100 dips. Okay, so this one just 4 layers. So it's likely you check back this generated learned model. They're probably not 100% representative of original data. You may find that compared to original dataset, there's still a few samples. Out of, let's say, 1,000, this value equivalent to H, but is in the different type. So in that way, we call misclassification. So we misclassify that sample into type 2. Actually, in reality, it is type 1C, for example. So that gives us understanding of purity. In reality, we cannot 100% sure purity is achieved, but we try to maximize this purity. Some research says tree-based model are not the best classification methods. I'm not quite sure, because tree-based, so there are several types of things: tree-based, distance-based, rule-based. So tree-based and rule-based can have some overlap, but it really depends on the dataset and the scenarios. So you may find some packages called CART, which is a shortened for classification regression trees. Okay, so you can use some packages which have this. So now we look at classification tree for a particular dataset. Okay, this dataset is first diagram on this page is a real dataset which has already been labeled. Okay, so it's a visualization on the existing dataset. So this dataset has 2 features: x1, x2. So one is XL, YXL. We can see that is the visualization. Okay. The 2 features or variables match with 5 different kind of labels or classes. First one is black. The second one is red, and then we have green, the third one, and the 4, blue one, and the 5th, light blue one. So based on this dataset, without looking this side, probably we can do something, use our common sense. For example, the red one is clearly x1 larger than certain value. Black one is x1 smaller than certain value, and the 5th class is some value certainly below some value. Okay, and then we can even handwriting some, given the value, we can even handwriting some value. Say, okay, green one is within this box, certain range of x2, certain range of x1. I got 3. The rest is blue, because blue is more difficult to describe. Okay, so we can see that given the use data mining model, x1 minus 1 minus x1 minus some value minus 2.7. So x1. Okay, x1. So x1 separate to 1, class 1. This means class 1, and the rest. Okay, the rest move to x1. So this means x1 smaller, and this means large. And then here has x1 smaller than 2.6, some here, then I know it's definitely 2. Okay, so I bet 100%. Probably this is a little bit overlap in this value, but anyway, it's 2. Okay, so finally we could do x2 on this condition. If this happen, and if it's larger than this value, and then I say if x2 minus 1.8, probably this one, that is 5. Okay, then we do further down, and at the end of the day we calculate, classified all these 5 classes. Yeah, 1, 2, 3, 4, 5. Yeah. So I hope this gives you a good understanding how tree can be generated given the dataset. In reality, it's probably more complicated and could be in multi-dimensional. So finally, we have give a recipe. So how we generate trees? Start at the top of the trees and use recursive binary split into growing trees. So which is top here, and then we recursively go back, and then go back and split to growing tree. Binary. But in reality, some trees may not be binary, so I'm not going to give that here, because it could be, in some case, could be in certain different ranges. Okay, this is binary, but it could be not only binary, but other probability. Okay, for example, one value have certain range, we could also split them, but the simplification of that is still binary. Even this x1 have 1, 2, 3, 4, 5, 6 ranges, we can still use binary to exclusive. So exclusive this one, exclusive this one, further exclusive one, and then we got that. We still can use binary to represent it. Okay, at each split, calculate the classification error rate. The error rate is a number of the version which are not the majority class in that region. So it's another way could be not 100 purity, so they are observation or record, then not in that class. So there are 2 common used variable to model the model purity. One is Gini index. You may have heard of it in the newsletter or newspapers or media. So this Gini index was originally developed for measure income inequality or wealth inequality in a country or region. And also entropy is very common as well in information theory, which describe is kind of method to model or describe disorder in the dataset, or randomness in the dataset, or model, or uncertainty in the dataset. So we are not going to give details of these measures, but if you are interested in that, you could spend some time to search. So in our package, this is quite simple. We have tree, and then that is in tree packages. So R is very common statistic packages, quite widely used, especially for economy people. Okay, there are a few remarks regarding classification tree. So, as we discussed before, if my dataset have 100 features, my tree could grow massively. Do I need a massive tree or not? So we sometimes need to cut the tree, called pruning. So because you may find that some subtrees could replaced with a fixed value. Or you can find in one tree, there are a group of subtrees, they demonstrate the same thing, or in the same model. So you can replace that subtree with a simple model. Okay, you can even replace a subtree with a function. So I'm not going to give that too much details, but just to remind you that first, we don't want the tree overfit. Overfit means my model is perfectly. May I go back to previous slide? Okay, maybe my model here is perfectly fit to the dataset I'm having on the left. However, as we know that classification is mainly, the tree is mainly for us to predict new object. For example, I got a new object come in. Okay, so let's say, okay, maybe we use class 1 as an example, which is x1 value equivalent to 0.18, for example. Just the x1 value is 2.6. Let's say 2.6 here. Okay, so if you use my current model, it's probably I will put them in either 4 or 5, depending on x2 value. However, it is x1. So this means that my prior model probably overfit, perfectly fit the current one, but not good enough for the new object come in. For example, I have the existing have, let's say, 1,000 record, but I got another 100 record, which I have x1 equivalent to minus 1.6, all belong to x1. Belong to one class, new object. I will all misclassified because I put them in the 4 and the 5. This is because my model is overfit. So the problem of classification, if they are too complicated, is often they go to a direction with overfit. And also too complicated, which means too big the tree, so it requires extensive computational resources. So we cut these trees. They are not very useful. So we got a different method to measure each subtree, how much they contribute to the accuracy of the model. So they are researching this area to improve. So end of the day, we want a very simple tree, but a good accuracy for predicting objects. Bootstrap aggregation. Okay, so this is to average over many trees. So if there are high variance in classified trees, for example, I got many trees for this dataset. Probably we can doing average of many trees. So give us a reduction of the variance. So basically, which means that we are not going to find one tree, but several trees for the same dataset and try to use the average trees. Random forest, which have a similar idea of bagging, which we just said before. So it has a slightly different with decorrelation of the trees. We probably will cover random forest in a different video. Thank you very much. I'll see you in another video. Thank you.